Okay, my amazing AP Chem students, we are on page 43. 43, make sure you are taking notes while you are watching the video. I will be collecting your packets on the day of the test and going through and making sure that I'm seeing your notes along with the videos being watched. So both need to be done. All right, titration. So here's the idea behind titration. We take an acid and a base. So either the acid's going to be in the burette or the acid's going to be in the Erlenmeyer flask or vice versa. Okay? But whatever is in the burette, we know its concentration and we're going to know its volume once we add it in there. So that's the important thing, is that the titrant has known values. Okay, so the titrant has known values, and we're going to use the titrant to titrate the unknown. And so everyone, the item that's in the Erlenmeyer flask that we don't know what its concentration is, it's called the titrate. Okay, so you have titrant, and that's what goes inside the burette, and then the one that we're like solving for, or the unknown concentration, that's what goes in here, and that's what we are figuring out, is the titrate. Okay, so the burette always has the titrant and it has the known values. The Erlenmeyer flask has the titrate, it's our unknown, and we're going to use the titrant to figure out what we need to know about the titrate. And there's two important parts of this, the equivalence point and the end point. So the equivalence point is when the moles of the acid equals the moles of the base. Okay, so like let's just say hypothetically that we got acid in here and base down there. It could be switched. So acid in here, base down here. Once I add enough acid that the amount of acid I added that has an equal amount of moles of acid, it equals the amount of moles of base down here, that's when you reach the equivalence point. Okay, so the equivalence point is when the moles of the acid equals the moles of the base. The end point is when the indicator changes color. Okay. Now, here's the important thing I need you to know. AP Chemistry, often they interchange endpoint and equivalence point. So sometimes they say equivalence point and they mean endpoint and vice versa. But usually they are replacing equivalence point with endpoint. The idea here is the endpoint is when we see a color change, and that indicates that we've reached the equivalence point, but that's only if you've picked a good indicator. You need to pick an indicator that changes colors at the equivalence point. So as we're looking at examples today, if it says that the endpoint was reached at blah, 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 then you can make the assumption that at that point the moles of the acid equals the moles of the base, because they must have picked a good indicator. So we're going to turn the page. So, quick review on pH scale. A pH of 7 is neutral. pHs less than 7 are acidic. pHs greater than 7 are basic or alkaline. That's another name for base or basic. Okay. And I want to pick an indicator that changes colors when an equivalence point is reached. So here's how I can tell what's going on with an equivalence point. So first thing, where I'm measuring the pH is always down in the Erlenmeyer flask. Okay, so like here's like pH probe. Okay, like I am measuring the pH of this. I'm never measuring the pH of that, because that's just going to stay the same. It's never going to change. Okay, so I'm measuring the pH of what's down here, the titrate. Okay, so do you see how the titrate started with a really low pH, and then over time we got a steep increase, and then it kind of leveled out. So I know a couple of cool things. The first thing I know is that in the Erlenmeyer flask, it was an acid just because there was a low pH to start off with. And I must be titrating it with a base because the pH is increasing as time is going. So the titrant is a base, the titrate is an acid. The other thing I know is that it's a strong acid because I have a low pH that I'm starting with. So if you start with like 1 or less, really somewhere in there, if we have a low pH, that means it was a strong acid. And if you end with a high pH, then you were titrating the strong acid with a strong base. Okay, now look at this one. See how it's still an acid, like we started with an acid, but it's not, the pH isn't really down low, it's kind of up a little bit higher. This means that we started with a weak acid, so our titrate, down in here, our titrate for this curve was a weak acid, and I was titrating this titrate with a titrant that was a weak base, because see how it ends with a pH that's higher but not as high as there. So this would be a weak base. Okay. So then what do we have down here? Strong acid being titrated with a weak base. And then here we have a weak acid being titrated with a strong base. Okay, the equivalence point is in the middle of this change. Okay, so like, see how slow change, slow change, slow change, and then drastic change. And if you go right halfway, the best you can, halfway in between, that is the equivalence point. Okay, so there's my equivalence point. And so then down here, my equivalence point is like right there. Equivalence point. Okay, and then my equivalence point, and my equivalence point. So I want to, if this is what's happening, a strong acid, a strong base, I want to pick an indicator that changes colors at a pH of 7. I want it to change at my equivalence point. If I have a strong acid and I'm titrating it with a weak base, then I want to pick an indicator that changes colors at a pH of around 4 in this scenario, 7 here, and then above 7, like 8, maybe 9. Like that's where I would want my indicator to change colors. Okay? And that's the end point, is when it changes colors. Okay. We are looking at page 45, but we're actually, we're going to skip a couple pages, we're going to come back to it. Will you please go to page 47? And this is what I want you to add. Okay, you need to know there are 6 strong acids, and you need to memorize, you need to know these 6 strong acids. We have, it's like a hyperchloric acid, I think that might be the name. Hydrochloric, hydrobromic, hydroiodic, and we got a nitric acid and a sulfuric acid. Okay. Let me get a periodic table. Okay, hopefully you have those written down. So, these three, chlorine, bromine, iodine, they're all in a row. Chlorine, bromine, iodine. So put hydrogen in front of those three, strong acid. Then you have nitrate, because if you take an H plus and you put it with NO3 minus, that's how you could get this nitric acid. Then here, if you take two H pluses and you put it with sulfate, which is SO4 2 minus, then that's how you could get sulfuric acid. So those are the 6 strong acids, and strong acids along with strong bases, when we do a net ionic, they separate. They separate into the ions, just like this. So this one would separate into H plus and iodine minus. This one separate into H plus, Br minus. This one's going to be an H plus and a Cl minus, and then an H plus ClO4 minus. Okay? So if you have a strong acid and it's a complete or net ionic, these ones separate. If it's not one of the big 6, then it's a weak acid, and weak acids do not separate into their ions. Okay. Strong bases. Strong bases are easier because you don't have to memorize them. What you need to know is that if you have a group 1 or group 2 metal with hydroxide, then it's a strong base. Okay.
Teachers, we pardon the interruption. Can we please have all applicants for Sterling Scholars report to lecture hall B right now? Thanks.
Here's 2 examples. Sodium is in group 1, and it's a +1, and hydroxide's a -1, so that's a strong base. So NaOH. Calcium is in group 2, and it's with hydroxide. Calcium is a 2+, hydroxide's a 1-, and so that's a strong base. But these strong items, if you're doing a complete or a net, they would separate. Okay. This would be calcium 2+, and you'd have 2 hydroxide minus. All right. So with that in mind, go back to page 45. We are going to write a balanced net ionic reaction that occurs when HC2H3O2 aqueous is combined with NaOH aqueous. All right, so this is a neutralization reaction. This is an acid. It's starting with hydrogen, so that suggests it's an acid. And then we are ending with OH, so this is a base. And whenever you have an acid that reacts with a base, you get water, H2O, liquid, and a salt. Okay, let me explain where the salt comes from. This hydrogen is combining with this hydroxide, so 2 hydrogens, 1 oxygen. So that's where this is. Sodium is now by itself, and C2H3O2 is by itself. If this is an H+, then it's C2H3O2 minus, and if hydroxide is a minus, then it's sodium plus. So those things are going to combine into an ionic compound, which is a salt. And it was a +1 -1. But sodium, our solubility rules, is soluble, so then I would put aqueous with that. Now, this is not one of my big 6, okay? Not one of my big 6, and so even though it's aqueous, when acids or bases are weak, we don't break them apart. So I would keep this together. HC2H3O2, aqueous. NaOH is a strong base though, so I am going to break that one apart. Na plus aqueous, OH minus aqueous. If it's a solid, a liquid, or a gas, we don't break it apart, so H2O liquid stays together. And then if it's an ionic, it's a metal and nonmetals, and it's aqueous, and we do break that apart. So Na plus aqueous, C2H3O2 minus aqueous. That's my complete ionic. I get rid of my spectator ions for my net ionic, and the only spectator ion is sodium. So my net ionic would be HC2H3O2 aqueous, OH minus aqueous turns into H2O liquid plus C2H3O2 minus aqueous. Okay. Alrighty. So everyone, during class, what we're going to do is that we're going to then use this complete ionic to figure out what our concentration of moles of sodium hydroxide is. And really actually we're going to use this balanced equation up here. So we want concentration of NaOH, and that would be moles of NaOH divided by the volume of the solution. Okay. And we're going to use the equivalence point to figure out how many moles of the base. And then we do know the original, the volume added was up there. Okay, so calculate the molar concentration of this two nitrates. Yeah, exactly. So we have our 10 milliliters, but this is the acid. And then we're going to use this to figure out our equivalence point. And then once we have that equivalence point, then we're going to be able to figure out the concentration. And my equivalence point is happening, right about there-ish. And so then we know what our volume would be. Okay, so we will do that during class. All right, everyone. Thank you for your hard work. I'll see you in class.